Okay, going from the result we had last week, we're going to do the u substitution again. There. I got u equals r squared plus x squared, and then I want to derivatize, take the derivative of both sides. I want to implicitly differentiate. So the left side I get du, and then here r is I get 2r times dr. X is a constant. This quantity is a constant, and so the derivative of x squared is just 0, because it's constant. So I have u and I have du. Okay, this guy right here I can solve for dr, right? Because I want to substitute u in for r squared plus x squared, and then I want to substitute in for dr to get rid of dr and have it written as in terms of du. So I can rewrite this guy as dr equals du over 2r. And so when I plug those guys in, when I plug this in for dr, and I plug this in for r squared plus x squared, I get that the electric field is going to be 2 pi k x sigma times the integral. Dr in the numerator, I have r times, and I'm going to substitute du over 2r in the numerator, divided by, denominator I just have now u to the 3 halves, right? And then I can simplify things. The r's cancel. This 2 is in the denominator, so it actually cancels with that 2 out in the numerator, right? And so when I do that, I get that the electric field is pi k x charge density times the integral du over u to the 3 halves. And we can do that integral. But we got to be careful here, because our limits are no longer from 0 to r, because we're not integrating with respect to r. We're integrating with respect to some new variable u. We could just figure out this result and then plug everything in back for r at the end, but to do it the big kid way, we got to look at this guy. Okay? If we're integrating from r equals 0 to r equals big R, well, when r equals 0, what does u equal? X squared. So when r equals 0, but then we do our u substitution, we then have to say, well, when r equals 0, u, because we're integrating with respect to u now, u actually equals x squared. So we go from u equals x squared to when r equals big R, what does u become? Big R squared plus x squared. So from u equals x squared to u equals big R squared plus x squared. Again, you're not going to have to do this in this class on the quest assignment. You're not going to have to probably do this on the... You will have to do u substitution in your calculus class, though.
Oh, man. I thought I was done.
No. You're never going to be done with it. And so I'm going to rewrite this because I like rewriting stuff to make it less mentally taxing on myself and easier to do. Integral from... Now I'm just going to write x squared to r squared plus x squared. And I'm going to rewrite this as u to the negative 3 halves du. I find that easier to do than just 1 over u to the 3 halves. Now we just use the power rule. That's like the first thing we learned when we started doing integrals in this class, just using the power rule. Pretty simple. The integral, again, simple. The work leading up to it, the physics leading up to it, not so simple. Right? That's the hard part. The actual integral isn't that bad after we've done our u substitution. And so what's the integral of u to the negative 3 halves? U to the negative 1 half over negative 1 half. Make it easier on yourself. Don't skip steps. If you can skip steps, that's fine. But I don't like skipping steps. I'm going to add 1 to the exponent, and I'm going to put it over that same value, right? And then evaluate that from x squared to r squared plus x squared. And then I'm going to rewrite this again because this is a compound fraction and my brain doesn't like compound fractions.
And why'd you wait with them?
Get out of my house. And so this is going to be, I divide this by a negative 1/2. So I think Timothy was jumping ahead one step, because then I have 2 negative 2 over
The square root of
u to the 1/2, or the square root of u. Yeah. I'm going to write it as u to the 1/2 though. I did that correct, didn't I? Squared plus x squared. And now I can evaluate this at my limits, right? So whenever I use the fundamental theorem of calculus, pi k x sigma times, what do I got? I got negative 2 over r squared plus x squared minus a negative 2 over x squared to the 1/2. Right, this is to the 1/2. Right? I'm not skipping it. Is that incorrect?
No, I'm correct.
Okay. Yeah. Notice I'm not skipping any steps because I have a tendency to mess up with my algebra. So how do I avoid messing up? I literally just write out every single step. So I evaluate the limits. Notice, yes, this is x squared to the 1/2. We all know that's just going to be x, but I'm not going to do that until the next step. So then the electric field is going to be Coulomb's constant times pi, or pi times Coulomb's constant, times x times sigma, times negative 2 over r squared plus x squared to the 1/2 plus 2 over x. Right? Okay, and then I'm going to.
And can it be either positive or negative 2 over x? Because that's the square root of
Yeah, let's just. Is it, x is going to be positive here.
Alright.
Technically, yes. Technically, yes. Notice, that's a good point. On the other side, at the same distance, negative x, the same thing would be going on, just in the opposite direction. Yeah, we're talking about this positive x coordinate right here. Good point, though. Good point. All right. And then I'm going to reorder this, just so I have a nice, neat little expression here. And I'm going to go ahead and put the radical there. So the electric field is going to be pi. Am I getting all those right?
Can we pull out a negative 2?
Okay. What's that?
Can we pull out a negative 2?
Or I could just reverse pi k x sigma times 2 over x.
Oh yeah, but I'm saying just pull out a 2.
Oh, pull out 2, yeah. You pull out 2 pi, and then you have 1 over x minus 1 over the square root of r squared plus x squared. Right?
Does it need to be simplified more than that? Does it seem like
To get to the result that we want, yeah.
Because you can do.
And I'm also going to take k and express it as 1 over 4 pi epsilon naught.
You can do the least common denominator and then.
We don't need to do that. We don't need to do that. But yeah, if you wanted. But what I'm going to do is substitute. I'm going to have 2 pi x sigma times 1 over 4 pi epsilon naught. So there I'm just substituting Coulomb's 1 over 4 pi epsilon naught for Coulomb's constant. And then times the same thing, 1 over x minus 1 over square root of r squared plus x squared. And when I do that, pi cancels. That 4 becomes a 2. Right? And here's the result that I'm going to use to come to the final result. Then I get x times the charge density divided by 2 times the permittivity of free space times 1 over x minus 1 over the square root of r squared plus x squared. Make sure that's right.
What a handsome equation.
What a handsome equation, yes.
You couldn't have done this all in your head?
And then I'm going to distribute, and again, you'll see why. Timothy, yes, if you're looking for a numerical value for the electric field in this situation, you can just plug in numbers at this point, yeah. But I'm going to go ahead and distribute the x over both terms. Again, for reasons you'll see in a second. And so when I do that, I get sigma charge density over 2 times epsilon naught times 1 minus x over square root of r squared plus x squared. So that's the most simplified you can get, the result here. Okay. Now, as I pointed out before, though, we're going to use this physics to calculate the electric field due to a sheet, an infinite sheet of charge. And I forgot to do this. I should have done this. Woo!
I'm sorry.
Why'd you drop that?
I know. Can you settle down, please?
I just get super rowdy whenever we're talking about electric fields.
You went through static electricity to pull that down, right?
Have you ever seen things like this?
Almost.
This is a demonstration capacitor. Sorry, let me get in front of the camera. This is a demonstration capacitor, but ones that are using like camera flashes look like this. Little tiny ones, like this. They're little cylinders. See that at home? Now what, and I'll do this whenever we do our unit on capacitance, I'll cut one of these open. What this is, it's not actually cylindrical until you take 2 conducting sheets, which are then charged. And they're conducting sheets, really long strips, and you separate them by a very thin piece of paper, and then you roll them up. You roll them up into a cylinder. Okay. Each of those sheets acts like an infinite plane of charge, because when you do that, what you're interested in is the electric field between the 2 sheets that are separated by a very thin piece of paper, thinner than your normal standard paper. And so the distance away from the sheet within that little piece of paper is very, very small in comparison to the actual area of the paper. Does that make sense? And so what that means is that we can approximate the area of that sheet as being infinite in comparison to the distance between the 2 sheets of charge. So for the dealing with capacitors, we don't really worry about this electric field. We worry about what this electric field becomes once the radius of our cylindrical sheet is approaching infinity. And so as R approaches infinity, can anyone tell me what this electric field approaches?
Sigma over 2 epsilon naught.
Sigma over 2 epsilon naught. Let me put a red box around that. That's real important right here. This is something you want to commit to memory. This is not on the formula sheet. But you will use it on the AP exam. You will use it on the test over this unit in this class. You will be using it anytime you're dealing with capacitors. The electric field away from a very large sheet of charge, as long as the distance here, keep this in mind, as long as this distance is very, very small in comparison to the area of the sheet, as long as that is true, the electric field is extremely close to this value. The charge density, which you can just determine by knowing the charge on the plate or on the sheet, divided by the area of the sheet, that tells you the charge density, divided by 2 epsilon naught, that's the strength of the electric field. Yeah.
Can I just use this whole process to figure that out every time?
Yeah. Mm-hmm. You got to start with the hoop, though, remember?
Oh,
Yeah. Remember, that's how we started this, with the hoop, and that's our result. Something interesting here. Can someone point out something that's very interesting? Very, yeah. What is the electric field dependent on?
I was pointing at something very interesting.
Oh, what? That printer?
No.
Yeah. What else?
2 epsilon naught.
Yeah. Those are just constants, though. Charge density can change. 2 can't change. Epsilon naught can't change.
Is that challenge?
That tells you that what doesn't.
Take one away.
What doesn't? As long as the distance is small in comparison to the sheet, the distance from the sheet doesn't matter. It's the same electric field strength. If we literally had, at this point here, a plane of charge that was literally infinite in extent, the electric field here would be the same as the electric field here, would be the same as the electric field a billion light years in that direction. The electric field would be the same everywhere, right? Yeah. Meaning that the electric field between two capacitor plates is constant and doesn't change, and makes it, until you get to the edges, then you deal with stuff that we don't even deal with in this class that you'll deal with if you're going to be an electrical engineer. You get edge effects that they get a little more complicated. But within this, the between those two sheets, the electric field is the same, regardless of how far away you are from one sheet or the other. Okay. So it's very interesting. The distance, x in this case, is not in the equation. The x is in this term. That term becomes 0 once the sheet approaches being infinitely large. So it's a very important, very important. Again, that is only if x is very small in comparison to the overall areal extent of the sheet. Okay. Now, when we have it, I'm going to say this, I'll just point this out. If we have a capacitor, we essentially have a sheet, a large sheet with maybe positive charge, and then we have another sheet that's the same size that then has a negative charge on it. And whenever you charge, when I attach wires to this guy and attach them to a battery, charge flows off of one because it's conducting. They're conducting sheets. Charge flows off of one sheet and onto the other, right? It acts like a wire briefly. When that happens, it's just a natural occurrence. One becomes positively charged, one becomes negatively charged. So the electric field between these two sheets points from the positive to the negative is constant, right? As long as, and I'm exaggerating here, these sheets are very, very close together in your typical capacitor. That electric field is relatively constant, as long as, again, they're very close together. What do you think the electric field of a capacitor is? If the electric field due to a single sheet of charge is sigma over 2 epsilon naught, what do you think the electric field between capacitor plates is?
2 sigma over 2 epsilon, or no, sigma over epsilon.
Exactly. It is 2 sigma over 2 epsilon. Because you have, remember, negative charges create electric fields that point towards them. Positive charges create electric fields that point away from them. And so you have 2 electric fields combining in there. They're going to be the same magnitude. These guys are going to have the same magnitude of charge, so they're going to form the same electric field, magnitude of electric field. And then by the principle of superposition, those electric fields just add in strength. And so you just double that. Again, you want to commit this to memory because we're going to be dealing with capacitors for the rest of the year. At the end of the year, we'll actually culminate in inductor capacitor circuits, which are like used to tune to radio stations and stuff like that. Good stuff.
What does a capacitor do? I'm so confused.
There's a lot of uses. The main use is stores electric charge.
It's kind of like a battery.
Yeah, it's kind of like a battery. Yeah. But then they're also used to smooth out electrical signals because we'll have 2 units that focus on capacitors within circuits.
Okay.
So.
Yeah, I was just curious because they keep talking about that.
Do you have a loud sound system in your car?
No.
Okay. If you have a really good sound system in your car, you have to put a capacitor in there because it smooths out the electrical signals. Otherwise, it sounds like crap. And for reasons that by nature, they'll discharge at certain times and charge at certain times based on the incoming and outgoing current. And so and it just happens by the very nature of what they do. But it's at the simplest case, you got 2 plates that you put them in a circuit, and a charge can flow. The charge can't flow through the plates, at least if it's working properly. And so you can charge them and store that energy for later, and we'll do that in this class. I got some cool demos, but first we want to deal with electric fields before we get to capacitors. It's good stuff, though. It's good stuff. All right. That's the end. This is the end.
No, all physics now.
Come
Time
on.
to go to sleep.
Oh my gosh, what is going on here? Oh,
Disobeying you.
And you told the projector that it's over too, so.
I guess so. Alright, let me just point a couple things out. Because there is a quest assignment for this unit, and it's a very important unit, very important techniques. So let me just read what I wrote for the physicers at home. This is 19th, right? Okay, so you'll begin the new quest assignment. It's called Charge Distributions and Electric Fields. You got a lot of time for this. It'll be due Sunday night. Okay, Sunday night. And we will be working on it tomorrow and Thursday. Friday, we are going to move on to new material. We're actually going to get to our first Maxwell equation on Friday. So you might want to glance through it. You might want to try some of the problems because the next 2 days you'll be able to ask questions. On Friday, we will be moving on. It will be due on Sunday night. It will count for a major grade. It's very important stuff. However, you're free to work together. You're free to ask questions. I'll help you through any of them, but I will be assigning a major grade for it. This will most likely be your most challenging quest assignment thus far because, as you notice, this electric field stuff is pretty complicated. And what complicates it further is that they're literally invisible. You can't see this stuff, right? You can only detect it indirectly or directly if you ever get struck by lightning, but hopefully that never happens. We'll be working on it in class up until and including Thursday. So ask questions, work together, and as always, online students are encouraged to join the Zoom meeting during class, which they obviously always do, except for Timothy when he's not here. Or it might be the opposite of that, I don't remember. All right? So, have at it. You got the rest of the period today, tomorrow, and Thursday. Work together.
How many online students are there?
I think like 5,
Oh, wow.
4 or 5. Yeah, not a trivial number, and yet you're the only one that has ever signed on to the Zoom meeting. I think, didn't Logan once?
Bradley,
Bradley has, yeah.
I
Only the in-person students. Huh, who would have thought? Only the in-person students. Only the people that elect to come to school are the ones that sign on to the Zoom meeting when they're not here. Huh.
So you said that epsilon naught was like a quantum mechanic value, right? Or
Well, it's defined classically, but I guess you can explain it quantum mechanically.
okay, well I was gonna say because like I was wondering like if it was just if you found it through quantum mechanics, like how relatively new like the electric field stuff would be then, seeing as though like that's such a critical value.
Yeah, I don't know. That's beyond the scope of this class and of my knowledge. We will see epsilon, because when electric fields are not permeating free space or empty space, then you still have permittivity values, but they're not epsilon naught because they change. Like when electric fields exist within the paper that's separating capacitor plates, or within glass, or within other materials.
Someone sounds like an alternate reality future movie.
There probably is some terrible B movie, sci-fi movie, or fantasy movie from the 80s. Something like that. I think I mentioned them last week. Red Letter Media, my favorite YouTube channel.
Movie, sci-fi movie.
What's it called?
Epsilon.
Epsilon.
1985.
95.
Oh, wow.
68% on Rotten Tomatoes.
Oh my gosh. Wow.
Better than I thought. 85% of Google users liked it too.
Oh my gosh. I'm gonna have to check it out.
I'm so smart.
Yeah, Red Letter Media is a YouTube channel. One of the shows they do is called Best of the Worst, where they watch like 3 terrible movies, and then they just rate which one's the best one. But it's hilarious because they're hilarious and they're very knowledgeable, so it's nice watch. It's fun stuff.
Is it true that conductors used to be called non-electrics?
Oh, I don't know.
How old do you think it is?
Non-electrics, conductors, or insulators?
Conductors, like they have, maybe.
I've never heard of that.
They can change it.
Why is the charge distributions of electric fields thing like just somewhere randomly in the middle of the quest list?
What? Oh, is it?
Yeah, it's just
Oh, dang it. Oh my gosh.
like most of the time it's either at the beginning or end. No, this one's just in the middle.
Quest updated, and I don't like their update, and it's been throwing me off. Let me fix that. I mean, get started, obviously, but let me fix that. Oh, jeez.
Yeah, I think like the first time I complained about it, it kept happening after that, where you would like have it not at the top.
Oh, really?
And I thought you did that just to annoy me.
Well, I did, but now I'll stop.
Yeah, they did used to